Hello, folks. So we're doing a rolling example, and we have a problem. You roll three different shapes with the same mass m and radius r down a slope, starting from the same height. Which object makes it down the slope in the least amount of time? Another way of saying, which object makes it down fastest or first? So our three objects are a ring or a hoop. So all of the mass is concentrated on the outer rim of this shape. We have a disc, a solid disc, and we also have a sphere. So if we go ahead and look up the moments of inertia for these shapes, we find that I for a ring or a hoop is going to be mr squared. For a disk, I is equal to 1/2 mr squared, and our sphere is going to have a moment of inertia of 2/5 mr squared. So different moments of inertia. And we have a drawing of our system over here. And if I think about this, I can talk about the torque on this shape. And since they all have some sort of roundness to it, whether it's a sphere, a disc, or a hoop, or a ring, they're all going to have a pivot point where we touch the surface here. So this is going to be our R. And then, of course, I have my force of gravity, mg. Let's use big M since that's the total mass. We're always going to put the force of gravity right at the center of mass. That's another useful thing that the center of mass provides. It allows us to place the weight at a very specific point. And so if I look at this r vector, right, I have an r vector kind of pointing like this. I have a force vector kind of pointing like this, r, f, and so the angle between them, phi, would be like this, right? I don't like the way that looked, but I have phi like this. And that's going to be the same no matter what shape I'm looking at, right? So my torque here, R cross F, right? Well, we can just say that is R F sine of this angle, which is going to be phi, right? And actually, phi, just a by the by, phi ends up being 180 degrees minus theta. Since this theta and this theta would be the same, and I'm extending r past this, the extension all the way to r would be 180 minus theta. That would be my phi. Alright, so I have the same torque for all of these, same magnitude of torque at least for all of these. So how does that help me? Well, remind ourselves that we have torque equal to I alpha. If I'm just thinking about magnitudes, I can just leave it as this. Torque is equal to I alpha. Another way of saying this, we can say alpha is equal to our torque over the moment of inertia here. I have the same radius, so I have the same distance that I need to go here, the same amount of rotations I need to go, the same number of angles I need to go through. This is why it's a little tricky to use theta as an actual angle, physical angle in the problem here, as opposed to an angular displacement. But what I'm saying here is that alpha, right, if I think about delta theta, that has to be the same for every single shape since they have the exact same r and the exact same path that they need to roll through. Delta theta is going to equal omega I times delta t plus 1/2 alpha delta t squared. Well, omega I is 0. We're starting from rest at the top of this hill every time. So alpha here is actually equal to, alpha is equal to 2 times my delta theta, right? My angular position here, not talking about this angle of the slope, but the angular position that I'm rotating through in my object, divided by delta t squared. Right, so now the last thing I want to say is that I have the exact same delta x, right, the same distance I need to go through, the same, if I'm unrolling this circumference, right, I can talk about, the delta x that I need to pass through. I can really say that that's equal to delta x over r is delta theta times delta t squared. That's now equal to tau over I. So now it really just rests on solving for delta t here, right? Delta t is equal to the square root of 2 delta x. Ooh, that's bad. Delta. 2 delta x times I over r tau. Close the square root. Since tau is the same for every single object that we're looking at here, right? They're all going to have the same mass, the same weight, the same force. They all have the same radius. So they have the exact same torque that we've calculated. They have the exact same distance that they need to roll through, and we just said before, maybe I really should have changed these. These really should be r's because they're the total radius of each shape. They have everything the same here except for I, right? I kind of is the only thing that's different here, right? I is different. So delta t, right, the time it takes to roll down this ramp is going to be proportional to the square root of I, which means the smaller I is, the smaller delta t is. The larger I is, the larger delta t is, right? So which one has the largest I? Well, it's the ring. It's the hoop. This one takes the most amount of time to get down the ramp. Which has the least? Well, it's our sphere. Our sphere actually goes down the fastest, right? Because it has the least amount of rotational inertia, moment of inertia here. And our disk is somewhere in between. So if we're going to go first, second, third place here, we have first place for the sphere, second place for the disk, and third place for the ring. All right? So that's a quick example of how to use torque, how to use moment of inertia to talk about a physical system here. All right? Thanks for watching, and if you have questions, you can always email me or come into an office hour. Have a good one.